We have been discussing and deliberating on the ideal gas law where molecules do not interact. We have done monatomic gas, which has given rise to an important expression of entropy of translation due to translation degrees of freedom, which is Sackur-Tetrode equation. Then we did diatomic. Everywhere we had certain payoff. In the case of diatomic molecules, we did the vibrational degrees of freedom, which though for molecules do not directly affect the thermodynamics, but the vibrational partition function model as harmonic oscillator with the Schrodinger solution from Schrodinger equation gives us the expression of the entropy and free energy and specific heat, which turns out to be extremely important in context of the specific heat of solids and crystalline and amorphous solids, and that is the way to think. Then we did polyatomic, but however all these ideal gas, the molecules could be rich in internal structure like in polyatomic molecules in water and methane and sulfur dioxide or methanol. However, they are non-interacting. That means the molecules are modeled as phantom things. They can pass through each other. They do not see each other. Now, in a high temperature and in low density, the majority of the contribution to phase space or to partition function comes from non-interacting part. So, this high temperature or low density gas works out quite well. You know, this ideal gas is not a poor approximation. Yes, it breaks down, but as soon as you enter in dense liquids, dense gases, or the liquids, then these non-interacting limit doesn't work. And it was very, very difficult. So, you know, people realized that very quickly, and they were trying to get around it by these solids. They get around by doing quite a bit by normal mode approximation, like it was done by Einstein and Debye. Then in the quantum cases, these Bose-Einstein statistics and Fermi-Dirac statistics, that was very useful by explaining superfluidity, but that was also again we did not do to consider interactions. There we went to a representation, and where we could do the, like, you know, in statistics it is just non-interacting particles in both statistics. Fermi-Dirac statistics is so important describing electron gas, but there is free electron gas. We did not have to take interaction into electrons at all. It was like that till 1935-36, but in 37, however, a very significant development took place, and that came from Joseph Mayer. Mayer realized that the difficulty. Mayer realized one very important thing, that in order to understand the real gases and in order to understand gas liquid transition, he was not thinking of liquid solid transition. That was far from his. You know, he was really just trying to do real gases, dense gases, because you know from van der Waals, equation of state. We know from van der Waals equation of state that if we can, plot pressure against density, then this is the part, very low density part, 0, very low density part goes like ideal gas, then it bends and then it undergoes a phase transition. Now, if I think of A, then ideal gas, that goes over like that. This is the ideal gas. This is ideal gas. But this is real gas. This is how real gas real. So real gas bends from here, then it bends like this, and then it flats. This is the coexistence, and this is the liquid. However, van der Waals, when tried to describe this behavior, it is a wonderful equation, van der Waals equation of state. He got something like that. That called van der Waals loop, which Maxwell fixed by doing the Maxwell tie line. And this what we call spinodal and all this kind of stuff. We don't want to get into it right now. However, The important thing is that this departure. So Mayer was interested to describe this departure, the departure from the ideal gas. And Mayer, just like Van der Waals, see before that Van der Waals did that. Van der Waals took it in attraction and repulsion of molecules. So Mayer already knew that how to proceed. He knew that we have to take the molecules, even if they are spheres, they attract each other in an intermediate distance. Very far, of course, they don't interact. And when they come very close to each other, bang, they are repulsive, because that's the overlap of the electrons. So his famous equation of state that P plus A by V square V minus B equal to RT, the Van der Waals equation of state, where A talks of attraction, B is the size of the molecules. What is the size of the molecules? That is nothing but because they repel each other, the repulsion defines the size of the molecule, diameter of the molecule. So Mayer knew that. Mayer knew that this is the way to go, that I need to have attraction, and at an intermediate distance I need to have repulsion, is a very short distance when the molecules touch each other, and they have to, the interaction has to fall to 0 when they go further. But how do you go about it? Van der Waals did it phenomenologically, remember. He said, okay, the total amount of volume accessible to a molecule is total volume minus the volume of individual molecules, and then when a molecule going to hit the wall to define the pressure. Remember, he was still following the Maxwell-Boltzmann kind of a kinetic theory picture of pressure, that pressure comes because molecules interact, molecules go and hit a wall, and that molecule is pulled back because there are certain other molecules near it which attract it. So the ideal gas, it would have pressure P. Now that pressure gets decreased and volume get decreased. Okay. So basically what he wanted to add it, okay, I want a effective pressure P and a effective volume P, so that I get it RT. So still working around PV equal to RT, ideal gas law. But then he said, okay, the V actually is little reduced, and the pressure that I really get, that pressure would be, if I want to get the ideal pressure, then I have to add this term to get the ideal. So I want to write PV equal to RT, but P and V are different because of the interactions. So he got that's the logic he gave to get the Van der Waals equation of state. But that will not work, right? Because we now need to we need a molecular description. We are talking of microscopics. We are going to have not this kind of hand waving argument, which works reasonably well, but still hand waving. We want to have real molecules, real interaction potentials. That how do you go about it? There's nothing there before Mayer did it. That's why Mayer's contribution is so important, and that's why you are spending a time on discussing Mayer's theory. Okay. We want a fully microscopic statistical mechanical analysis of interacting many body systems. And what do we mean by interacting many body systems? Let again go down a little bit now and let us see. So I have a potential, this I described, that interaction potential, say UR between two molecules I and J, and this is Rij and this is Rij. Then the interaction potential I have in mind is something like that, and this is called Lennard-Jones interaction potential. So UR equal to 4 epsilon sigma by R to the power 12 minus sigma by R to the power 6. This is the attractive term, and sorry, this is the repulsive term because of the 12, and this is attractive with a negative sign in front. So this is the 1 over 12 part when they, and this is where the molecules kind of touch each other. So this is the molecular diameter sigma, and this is sigma. Then it zoom, the energy goes up. When they separate a little, then there is an attraction. This is called London forces because of the induced dipole induced interactions, and I cannot go into that. And then it goes like that. We will at one point of time talk of intermolecular forces, but this is the kind of thing that I have. One important thing to note, that this is a radial potential. that means depends only on r, there is no angle. So, these are just spheres, is the simplest possible thing. So, if we have this kind of interaction potential, then we want to so we have starts with intermolecular potential. So, given intermolecular potential, so I give you the Lennard-Jones, the simple one. Then we want to do calculate, we attempt to evaluate the partition function from first principles, like sum over energy levels, interaction over the e to the power minus beta is Hamiltonian, that is the thing. So, that was the thing that Joseph Mayer did, and we are going to do that. In the process, he introduced what could be considered first graph theory of liquids and gases, and that he did the cluster expansion, and he got a huge number of results that came out of these things. Not only that, that made the beginning of classical statistical mechanics, the most significant step after Willett-Gibbs, Boltzmann and Willett-Gibbs. So, it derived, it gave a derivation of virial coefficients. It explained many of the things of van der Waals, language of clusters, size distribution of clusters, which is so popular, and microscopic picture of gas liquid transition. All these things came out, and so next we this is interaction, but we already done that. Now, so let us start working now. We have the n number of particles, So, in a system I have box volume V, and I have n number of spheres. They are not too low density, and the spheres are interacting with that, with the Lennard-Jones potential, and this is the molecular diameter sigma. So, two spheres are teaching, that is sigma, and Rij is the distance, it goes little bit faster than drawn here. Okay. And this is the height of the attraction, depth of the maximum attraction potential, and this is epsilon. So, the this is epsilon, that epsilon is this epsilon. Okay. All right. So, we have this Hamiltonian kinetic energy plus potential energy, and we have to evaluate with that Hamiltonian, we have to evaluate this partition function, we have to evaluate this beast, and look at that. I have, these are vectors, I have n vector integration over position, n vector integration over momentum, I have Boltzmann factor 1 over n factorial, and I have h over 3 and the Planck constant. As we told in the very beginning, that this is a formidable thing of statistical mechanics to evaluate this integral. This is the holy grail of statistical mechanics, to evaluate the partition function. If I have partition function, I have everything. I have free energy, I have entropy, I have specific heat, I have compressibility, everything. But how do you get the partition function? That is the problem. So, whenever you try to do something so formidable as this one, the idea is to divide and rule, and we will divide and conquer, and we will do that divide and conquer thing. Okay. So, then this is a partition function. If I get the partition function, I get the free energy, and I get the pressure and the equation of state, and the beta H, this thing now is H is written, this is the kinetic energy, and this is the potential energy is sum over. So, we assume that potential energy is pairwise additive, that is a very good approximation, but still a simplification, it goes wrong now and then, but it's perfectly okay with to start with this pairwise additivity. That means total potential energy can be a as a sum, or look at the notation here, so that we avoid double counting. We have to say that the I and j runs like is greater than equal to 1, but j is greater than 1. So, the terms will be written as u12, u23 plus u34 plus u13 plus u34 or 14, like that. That means you have or rather 13, 14, then 23, 24, like that, so that I do not count it twice. So, with this UN now formidable because of the Lennard-Jones, I set out to calculate the partition function. What do I do it now? So, I write down the partition function again, putting the whole thing here. Now, I immediately notice in a classical partition function, I can evaluate this part like I did in translational monatomic gas, because they decouples from that and they decouples among themselves. Momentum of one particle is not coupled to momentum on other particle, and x coordinate is not connected to y coordinate. So, it is px square, py square, pz square for one first particle, second particle, third particle, and I can do that integration. We did that just exactly like that we did, and that gives I know this part that we did in ideal gas law. And we know that part is due to second-order equation. So, you can see the decomposition of beautifully decomposed since free energy is the log of that term, they already start decomposing log this part, the ideal gas part and the interactive part. And this part is called the configuration integral, is now contains all the non-trivial contributions, all the non-trivial contribution of the effective interactions of the system. This part which gives makes gas to condense to liquid, that cause liquid to go to crystal, this interaction part with let you and me to talk and walk around. So, that is all in this configuration integral. So, we are now going to find out how to evaluate that thing, and we just rewrote that there are this is sum e to the power minus. I can write now that quantity I write as a product, because e to the power minus a plus b is e to the minus a dot e to the minus b. So, this is sum, this sum goes to product, and this is just a notation, no big deal. Now, difficulty of doing this integration was people tried that this thing the potential unfortunately goes to long distance goes to 0, and potential goes to 0 e to the power minus that potential that goes to 1, and that is bad news for us, because I have to integrate and something which is less than 1, because e to the minus beta u can be less than 1 in short distance, greater than 1 in intermediate distance, but then tapers off to 1. It is a very complex function, e to the power minus beta u ij. So, Mayer did a brilliant thing at that point, and he said, okay, these integrals that I am trying to do in configuration integral are not convergent, because they are giving a lot of difficulties, because in the long separation they are coming out with a contribution unity, contribution 1, and that is not a good thing for me, because I cannot do, I want to separate it out so that I do not have to worry about the long separation part. So, introduce this function which is called Mayer F function, which is f. So, this is called Mayer F function. He said, okay, let me write the following way. I write f rij e to the minus with the minus 1. I take out the minus 1 part, so that now r going to infinity, rij going to separation between two molecules becoming very large, beta ui rj going to 0. So, this quantity going to 1, and then this quantity going to 0, f rij going to 0. So, this is embodied here. So, it is a beta rj which was causing the problem was going, and this saturating it was this is 1. So, it was stopping at 1, but now I have taken it out 1. So, it start negative. It was before that it was starting when it was infinity, you at short distance infinity, it was starting from 0, and is intermediate distance when there is attraction is becoming greater than 1. Now, I am taking it out. So, it starts from minus 1 and it goes above, can go above 1 or so depending on the depth of the attraction, but now in long distance it is going to 0. This is 0, this is a 0 line, it is going to 0. So, it is very good. Now, I can try to do this integration. Then what Mayer did was something really very interesting. He said, okay, let me write the partition function now, which the partition function is written as the product of these now only have positions, and e to the power minus beta u rij, as I said, is the product, and f ri. So, this quantity is now replaced as 1 plus fij. This become, because fij is this quantity minus 1. So, this quantity 1 plus f, which is written as 1 plus f. So, my canonical partition function now becomes like that. And then the beauty is that now I can decompose it. Now, I can do that. Look, I write it out like, let us say the 3 particles or 2 part 1 f1 2 1 plus F2 3 particle system or 3 1. Just let us consider that we have n equal to 3 particles, then I have first term is 1, second term is F12, F123, F31, F12 plus F13 and F23. Then there are another set of particles terms that are binary terms F12, F23, F23, F31, but there is one term which is F12, F21, F3, all three are present. So this is now done here, symbolically written, one comes, then these are these isolated terms which are 1 2 plus 1 3 plus 1 4, then these are the product terms. Now may I introduce the following to beginning of the graph theory, and this is, as far as I know, the first application of graph theory to statistical mechanics. He said, okay, first term which comes with the value 1 is just 1 dot. Second term, which is this series of terms, are 2 dots and joined by line, and line is the Mayer function. Then there are 3 dots and they are chain, and there are 3 dots and I can form a ring. Total number of and then he said, okay, let me now consider that total number of single particles as M1. This guy, which is a cluster of size 2, total number of particles that M2, then total number of particles of then these things, we call them M3, which includes this one. So now ML is the number of clusters of size L that does not make any distinction whether there is a singly connected, doubly connected. So, and then I can of course write n equal to element. You can beginning to see something, that is kind of things we played the game in canonical, going microcanonical to canonical, that kind of game we are going to play, because this is a constraint that will come in my writing a partition function, and I will do exactly like that. I will try to write a total number of ways I can distribute particles to these clusters, and then you can imagine that I can have the constant and I will get a Lagrangian undetermined multiplier. That is the game that is played, and then we have done it before. Then what Mayer did, okay, he did something very smart. He said, well, I have defined L number of ML at a number of clusters of size L. Now, can I now give a weight to a cluster of size L? He said, okay, I will do that, because he looked at the partition function, he saw that they are nothing product and A of Fij. So now he said that I will now have all the integrals which are connected, all the connected diagrams. That means, say 3 particles will be F1 2, F2 3 plus F2 3, F3 1 plus F3 1, F1 2 plus F1 2, F2 3, F3 1. So these are all 3 particle clusters. They are all connected. They are chain diagrams like these, and these are chain diagrams and ring diagrams. So he said, I put them all together, and the weight of these to the partition function, I call it BL, the cluster integrals. And then I define it as 1 over L factorial V. V is very important for reason I will say, for normalization, and then I have integral over d1, and I have the product. This is the product F1 to F2, that is the product. Then this is the sum, and this is the sum 1, 2, 3, 4. You just write it down and you will see it work out beautifully. Then BL are sum of all these things. So for one single particle there is L factorial V and there is nothing inside, dr1 I get 1, 2 particles is the ring, I can do that, and I say 1 over 2 V and dr1 do fr1 2. Now I can change my coordinate system, I can go to particle 1 and say then this becomes, already it is 1 2, this becomes 1 2, then I get an integral and then say r1 to ir. So dr4 as vr, the dr1 is not involved, I can integrate out, and that is a coordinate origin, I get a v, that cancels this v, so I get this quantity. B3, the exactly what I wrote down, this is the B3. What is the advantage now? The great advantage he achieved by decomposing it, and then once you decompose like that, you sum contribution to configuration integral, because that is what we are trying to do, the total configuration integral of clusters of size L. So it is a graph theoretical decomposition, that becomes this quantity. So, there are ML clusters of size L, and they come with the weight VBL, and then I VBL to the power ML, because ML is the number of clusters of size L, and clusters of size L, all of them put together, and they bring together a size ML. So, that becomes that, and this part is I have ML cluster, each of them L. So, I can now in classical statistical mechanics I can rearrange them. So, L factorial is the way I can distribute, and there are ML such clusters. In my system at any time there are ML such clusters of size L. So, the L factorial to the power ML. So, that becomes that. Now comes the important thing, that how do I now, so but these clusters can be many different size, and they are splitting. They are not real clusters, they are clusters which are we call mathematical clusters, because they are connected by this bond, F bond, Mayer bond. So, every arrangement is possible. So, I can out of n fact a total n number of particles, how many ways I can form these clusters, that is n factorial by these just the combinatorics that you all of you have done in the school multinomial. So, now this is the weight of one set of ML, and that one set of ML I can do this is the number of ways omega, and then so I need to make the product of that, get the partition function, then the partition function is 1 over L factorial ML, and this L factorial this cancels, and n factorial remains here, and then I get VBL to the power ML, and the sum over all possible combinations of this kind, then I get this beautiful expression VBL to ML by, it is exact, and this is called Mayer partition function. Now, one can go do a lot in with these things. We still have not done one thing. So, that we have not calculated BL, we have not devaluated these things, that is what Mayer did. But in the process he introduced the cluster integrals. There is a recursive way of, if you know the BL, then these actually nothing but a polynomial called Bell polynomials, and then that is described in my book. Then one can have a beautiful relation, recursion relation between the and which allow between Zn plus 1 and lower series. So, we can build up the configuration integral, which is the total actually the non-trivial part of the partition function. We can, so if I know these cluster integrals, if I know the this called reducible cluster integrals, then I can calculate the partition function.